Next topic which we are going to be covering on this video is twist of thin-walled and open profiles. So we're still focusing on twisting profiles, so we're applying pure torque to the profiles, but now we're talking about thin-walled and open profiles. Before we go any further on this topic, it's beneficial to define what actually is a thin-walled and open profile. Well, thin-walled we define so that if you take a closer look at this cross section of this profile, we draw here we divide this into imaginary rectangles by drawing these lines in here. And if for each of these rectangles, if the ratio of the longer side divided by the shorter side, for example for the number 1, if the ratio is more than or equal to 10, and this applies to each of these sections, then the profile is considered as thin-walled. What about the open profile? Well, in open profile you are capable of touching each of those surfaces of the profile. So you can imagine that if you have a really long profile like this, you can actually go on any of the surface and you can touch these surfaces inside and outside by your hand. That means the profile is open. So now when we have discussed what does it mean that the profile is open, we can start taking a look on how can we calculate the twist and shear stress on this kind of profiles. Well, the formulas which we have used before for the shear stress and the change of the angle still apply for open thin-walled profiles. We just need to know how we can calculate the Ix, which is needed to calculate the twist angle, and the Wx, which is needed to calculate the shear stress. Well, let's start from the Ix. So in equation for Ix, we have 1 divided by 3 multiplied by sum of Si multiplied by Ti power to 3. So what are those? If we take a look from the previous video, in previous video for rectangular cross sections, we defined that the Ix is alpha times height multiplied by b power to 3. If we take a look at this equation, it has similarities with this equation for rectangular cross sections. Well, basically in the equation for second moment of inertia in thin-walled open profiles, the 1/3 is the alpha, and since the ratio of thickness and the width of each of these imaginary rectangles, the ratio is more than 10, we can see that from the table that we use for rectangles, we can see that if the ratio goes to infinity, so basically if it goes below or above 10, the value for alpha will be 0.333, and 0.333 in other terms is 1 divided by 3. So that is the alpha. What about the Si and Ti? Well, in order to define the Si and Si, we have to draw imaginary center line across the entire profile as shown in here. When we have drawn the imaginary center line, what we do is that we calculate the length of each of these center lines. So for example, S1. So the S1 in this case is 80 millimeters minus half of the thickness from here. So we have to reduce here this one, and we can calculate the length of S1. And from this equation you can see that in here we have S1. Well, what about the t? Well, the t in this case is the thickness of that said section there. So in here it is 4 millimeters. So we could call it T1, like that. Well, similarly, exactly the same way, we're going to do the same thing for all the other imaginary sections in here. Well, S2, for example, will be 55 millimeters minus 2 millimeters from here and 3 millimeters from here, which means that the length of our S2 is 50 millimeters. So this one here is S2, and then this T2 is the thickness of that section, which is 5 millimeters. And the same way for S3. S3 is that one there, and that one is T3. And that's how we just simply calculate the Ix second moment of inertia for thin-walled open profiles. Well, in order to calculate the section modulus for thin-walled open profiles, we first are needing the second moment of inertia. And to calculate the section modulus, we divide the second moment of inertia by the maximum thickness in this profile. And in this case, the thickest section is in here, and the thickness there is 6 millimeters, and we come up with the section modulus of this profile. That's how we calculate those ones.